I think we are ready to begin. Our next speaker is Leonid Fel from Technion, who speaks on Genera of numerical semigroups and polynomial identities for degrees of syzygies. So Leonid, pожалуйста.
Yeah, thank you. Thank you for invitation to participate in this venue and this great opportunity. My talk is devoted to the to arbitrary numerical semigroups and to study the genera based on the some identities that was derived several years ago. So I start with definition. Numerical semigroups is built by this linear combination of the integers with GCD equal 1, and neither of the elements is linear representable. This is a very general knowledge. The main notions that are used here is the multiplicity, the minimal generator. Embedding dimension is the length of the tuple, D1 up to Dm. The set of the semigroup gaps is denoted by delta M, is all these integers that cannot be represented by the tuple. The Frobenius is larger in these gaps. The genus of the semigroup is the cardinality of this set. And the Hilbert series is the generating function for the semigroups. By Hilbert's syzygy theorem, it has a rational representation with this numerator as alternating power sum with this powers with the degrees C sub jk that calls the degrees of syzygies. Beta k are the partial Betti numbers. Simply in this free resolution are the sizes of they are dimension of the modules, and the B sub m capital is the total Betti numbers. Several years ago, we have studied the so-called alternating power sum that are in the one and have proved that all the sum with its degrees up to the m-2 are diminished, and the sum with the degrees m-1 can be calculated. Is exactly this value with this pi m is the product of all the generators. It was very unexpected that this statement was very useful to calculate some interesting characteristic with small embedding dimension 4, 5, and 6. For example, to find the lower bound in the Frobenius and the genus and so on, and even more in the dimension 6 to prove the Stanley conjecture, so-called log concave conjecture in the unimodal distribution of the Betti numbers for the symmetric semigroups. Now the goal of the present work is the following: to go beyond this embedding dimension m for the degrees n larger than m, and to look what can we gain in this game. And it turns out that we encounter with the so-called genera. Genera means the power sum of this powers of the value of the gaps. For example, the G0 is the genus, simply the number of these gaps, and so on. We find the number of the independent genera and shows that the growth of the symmetry of semigroups, I mean in the commutative algebra, means the non-Hohenstein, and even more the complete intersection, gives the decrease of the number of the independent genera, and finish with the m-2 for the complete intersection. I will start with a so-called auxiliary section that will be useful in this further talk, but in the moment he has his own importance. It's very trivial, but very unexpected. It was published in this year in the Discrete Mathematical Letters, and this I start. Let us look on this polynomial. It is symmetric polynomial on this reals numbers x1 up to the xm. It is constructed in the alternating way with sum of the powers, sum of the in pair the powers, and so on. And it is symmetric because it is invariant under the permutation, I mean under the symmetric group Sm. And now this is a statement. A very interesting statement is the following. So it vanishes for all the degrees from 1 up to the m-1. It converges, can be calculated for the n equal m, with this high is the product of the xj, and 3 other is very important. For the n larger the m or equal the m, this polynomial is always divisible by this product. It's also divisible by the sum of this x when n and m are of different parities. And for the different parities of m, Pn has the flips from this positive to the negative. This makes us possible to make the representation in the following way. Why it was taken, I will show a little bit later. And from here and from this alternating signs for the polynomial, you can see that this polynomial t xm is always positive. Now it starts this mystery. What is the mystery? Let us define the power sum. Ek is powers k over all the 6m, and we will calculate simply according to this definition in 4 these polynomials, and this is 7 polynomials that I put here. Once more, I have calculated them so-called in vivo, but the structure is very, very interesting, and I have not seen this list, and I even has asked several of the friends over the world, and they say they also have not seen such sign. Now the polynomial, 7 polynomial here, they are algebraically dependent. I mean, we can twice decrease the independence. So every odd polynomial can be translated via the previously even polynomials. And this is end of the story, but not completely. After I have written these 7 polynomials, in some way I have reminded that 10 years ago we have studied with my colleague Rubinstein from Kansas the so-called restricted partition function. This is very known kind of the partition when you have the S positive number, you go to partite it in different integers dj, and it vanishes when a partition does not exist. And by this now accepted presentation of the partition function, it can be presented as a polynomial part and the higher Sylvester waves. And here I have this exactly the formula for the polynomial part of the partition function with this f small sub r. This is the exact formula. B is here is a so-called symbolic or umbral calculus. B will be transformed in this Bernoulli numbers. Now, if we go to calculate this FR, we have exactly this list. And now, when this list was presented in this Rama journal before 4 or 5 years. And now, if you look now on this list for this from formula and for list for the T polynomial, you see this exactly the same, apart the signs that are highlighted here and here, plus and minus are exchanged. And I don't know why. I cannot explain what form is coming, this very, very deep connection between the partition function, very naive polynomials that I have given in this previous slides. And therefore, I have stopped here with this conjecture that the polynomials that coming from this Pn are related to the polynomial in the partition function with this formula. This is completely technical part, but I would like to say that this is a very interesting question by itself. And now I will go to this main part of my talk, because in the talk, the T polynomial appears very natural. Now, by the definition of the Hilbert series, in generating function for the for the gaps, we have the relation f is a generating function for the gaps, and h is a Hilbert series. And by translation is in the following form, we go to differentiate this equation 8 r times. After differentiation, we come to the 9, and here is the derivative of the order r, and we can calculate it. And when we calculate it, we stack with this genera of the higher order with the Stirling numbers and also with the alternating sum. This is the way how to put into the games the genera. And from the other side, going to differentiate this part pi that includes the here we have this Eisenstein polynomial and so on. We arrive to the following formula. So for the n larger than m and equal to the m, we can write the alternating sum can be given by the formula with k, and k from 0 to the 6 is simply the linear combination of the genera, and t comes as a coefficient. The polynomial t comes from this previous section. Now, instead of the xi, here are sigma 1, sigma 2, and what means the sigma? Sigma means I have in the moment have defined it here. Sigma is a sum of this generator, and another one stuff is the delta. Delta is the sigma sub p minus 1 over t and p. Now, the coefficient here for the first glance are a little bit strange, but in the second glance, you can recognize that all the 6 formula, once more, all 6 formula have been calculated by this by hand. I mean in this mathematical software, because I know this formula for T, or 7 formulas. But I can recognize here such nice formula, or even more in the symbolic way. It will be written here, and this is a second conjecture, that the alternating sum, once more, alternating sum for the degrees larger than embedding dimension can be written with the coefficient chi. I have not called them modulus or something else, but what is very interesting, because this genera are the algebraic characteristic of this numerical semigroups, or associated to these semigroups, so-called the semigroup ring of semigroup ring. So the polynomial T, in my understanding, has much more deeper algebraic meaning than the simple combination of genera. Now let us go further and look onto this alternating sum as a simply independent variable that I have called zeta 1, zeta 2, up to the overall. They have the number of these variables is given by the total Betty numbers. And now I look onto this equation, onto this equation, and because I have only a finite number of the variables, I can take also the number of the equation and to look, can I find a relation between this K, or between the genera. Now, the whole business here is the following. In the 12th, this is algebraic equation when L sub K is 0 if K is less than m minus 2, is given by the formula if is equal m minus 1 and is larger, is given here. Now the study of the non-homogeneous equation with this n plus 1 non-homogeneous, when n variables goes back to the Bezout, Sylvester, Kelly, and Macaulay, and the main tool to handle with this problem is the elimination theory. So to build the so-called the multivariate resultant. Why is this very important? Because of this theorem of the very fundamental theorems is one of the versions is given in the Gelfand-Kapranov-Zelevinsky is the following: a resultant is a reducible polynomial over a ring generated by coefficient of the polynomial, which vanishes whenever all polynomials have a common root. Now it means that if we go to solve or resolve the system of this algebraic equation, we can come to this relation between this K or between the genera. It's very useful to rescale the variables by this root of m minus 1 from this product, and to arrive in this rescale way to the equation 15. And now we come to this first statement. There is this algebraic equation in Gm plus 1 variable, and the polynomial Rk is reducible over a ring of all these parameters. Once more, all the parameters means the K that is in the right-hand side of this algebraic equation, rescaled by the sum powers of these roots. The proof is very clear and can be done in several steps. On the first step, we go to eliminate the first variable psi1 and remain with bm minus 1 polynomial equation. What are the polynomial equation? We go to couple in the resultant the g1 with gj, and the second step we go to eliminate psi2 and so on, and in this way we come to the final results that give us this relationship, algebraic relationship between this genera or between the sky. Now there are some corollaries. So there are exactly GM algebraically independent genera because chi and j are related by the linear relations, and I can also make relation in any between any GM plus 1 genera, not necessarily with the first one. In the next transparency, I give you the example for this, the first non-trivial semigroups generated by 3 generators. Beta 1, beta 2 are 3 and 2, and the number GM for m equals 3 is equals 3. It means we have only 3 independent genera, and the simple algebraic calculation gives us this relation. The relation between G0, I means the K0 means K0 scaled by some square root of pi 3, kappa 1, kappa 2, and kappa 3. In other words, kappa 0, kappa 1, and kappa 2 can be taken as this independent genera. The same can be done for the 3 generated semigroups when we can couple together not the first 4, 0, 1, 2, and 3, but for example, 0, 1, 2, and 4. We also obtain the polynomial, the algebraic relationship, and this polynomial is not cannot be reduced. I mean, it is irreducible. Now, going with the growth of symmetry, by saying the symmetry, I means in the algebraic sense, we can look onto the associated semigroup rings and ask for this Hohenstein and non-Hohenstein type. In this language of the semigroups is called the symmetric and non-symmetric semigroups. By the statement of Kunz, they are bijection between the semigroup rings and semigroups. And now we can look in the symmetric semigroups, we have the relationship between these BT numbers and also between these degrees. This makes twice less the number of the independent genera. And so the genera can be written all this even part via this odd, and the number of this independent genera in the symmetric case can be given modulo 4. So independent number of the genera in the semigroups as 4q plus 1 is here, plus 3 here, and this is here. For example, we can look on the so-called the Brzezinski semigroup. It is semigroup, symmetric semigroup, but not complete intersection. It can explain, can represent all this chi2 via 4 independent coefficient k, or in the other word, in the genic. Now, in the last 5 minutes, I come to the very nice part this complete intersection. Complete intersection has this numerator in the Hilbert series. This exactly reminds the polynomial Pn. So here, relationship are very, very simple and naive. So the product of all these degrees in the complete intersection are equal to the product of the generator. It is known results, but what is much more interesting that the chi sub p is completely the polynomial t over p plus 1, and the number of the independent genera is m minus 2. What does it mean? It means very important thing. For example, for semigroups that are generated by two elements, all this k are given in very simple formula. All this genera can be calculated. We have not any independent part. By the way, you can compare it with the very known results of the Rödersch that has complicated calculation for the genera and can see that it is concise. But what is much more important that here is when we go to deal with the k coefficient, it seems much more easy to see. In this complete intersection with three generators, we have only one independent part, and you can see all this chi can be explained in this chi 0. By the way, to give this to give the formula for the genera by G0 is much more difficult, and the same is for the S4 with two independent, and here K0, K1 are here, and I go to finish the main two messages. The first one is the polynomial equation related k independent coefficient k read much shorter and much I would like to say much nicely than they counterpartner the genera of numerical semigroups, and can be seen in different examples for the non-symmetric and symmetric semigroups, in particular for this complete intersection. And this observation make me to suppose that Kp, so-called the combination, linear combination of the genera, has to have much deeper meaning from this commutative algebra sense than simply this relation. Here I will stop. My time is finished. Thank you very much.
Thank you, Leonid. Are there any questions? We have always a minute or two. If not, then I thank Leonid for his talk, and the next talk will start in 3 minutes.